Good afternoon, everyone, and welcome to the third in our February 2016 series of webinars related to nuclear waste. This afternoon session is on radioactive roads, transportation of high-level nuclear fuel waste in Canada. And this session, our sessions frequently have an expert presenter, a technical presenter. This session is one of the exceptions to that. This is not a expert or technical presentation. It's an overview and an introductory discussion of radioactive waste transportation issues in Canada. And we have lots of material to cover, and we have lots of work to do in this area. And it's great to see so many joining the session and joining in on this important conversation. So we're going to start, just as we always do, with the basics, a quick background context setting for this conversation. And then we're going to focus in today on the transportation of high-level nuclear fuel waste, and particularly focused in Canada, although we certainly borrow some analysis from other jurisdictions. We're going to talk about NWMO's plans, their reference plans, talk about some of the risks related to the transportation of radioactive waste, take a quick and very initial look at transportation routes, possible routes, and identify a couple of related issues. Then a first conversation about next steps. So nuclear waste, radioactive waste are generated at each stage of the nuclear fuel chain, from low-level waste in the several first links in the chain, uranium mining, refining, processing, fuel fabrication, to production of low, intermediate, and high-level waste at the reactor, in the reactor during electricity production. And then high-level waste is our long-lasting legacy from that fleeting benefit of electricity production. The high-level waste is the irradiated uranium fuel bundle. So it goes in as uranium and it comes out as high-level waste, nuclear fuel waste or spent fuel. And that happens because the uranium in the reactor core is bombarded with neutrons. It splits, fissioning takes place. As a product of this chain reaction in the reactor core, which is kickstarted for the purpose of generating heat to produce the electricity, it generates a couple of hundred different radioactive waste products. And therein lies the problem. Many of these products, many of these radioactive isotopes or waste products are lethal, are hazardous for very, very long periods of time. Some of them very short periods of time, but many of them have a half-life of thousands, tens of thousands, even millions of years. And a half-life is the amount of time that is required to reduce the radioactivity by 50%. Generally speaking, 10 half-lives to stable. So if you have a material like plutonium, a half-life of 24,000 years, 10 half-lives, 10 times around the circle for half-life, and you've got 250,000 years of a material that has to be safeguarded, isolated from the environment. Even low levels of exposure to these materials, to ionizing radiation, can be harmful. And the wastes have to be isolated from the environment, from people, from plants, from animals, virtually into perpetuity. So to date, the nuclear power industry in Canada has produced 3 million bundles, about 50,000 tons. Newest number, I think, is 52,000 tons produced to date of this high-level nuclear fuel waste, irradiated fuel. And that volume is expected to double over the next 30 years. The industry has had an intention since the 1970s to bury the waste in a rock formation. The 70s, 80s, and 90s, it was the Canadian Shield. Through, as of 2005, Canadian Shield or sedimentary rocks of southwestern Ontario. And that intention to bury the fuel necessitates the fuel being transferred transported from its current location to any eventual centralized site. The nuclear industry in Canada is organized as the Nuclear Waste Management Organization for the purpose of developing a facility for the long-term management of the irradiated fuel waste or high-level waste. So the Nuclear Waste Management Organization is made up of Ontario Power Generation, owns 90% of the fuel and has majority control of the Nuclear Waste Management Organization, Hydro-Quebec, and New Brunswick Power. Atomic Energy of Canada Limited also is a waste owner and makes some financial contribution to the Nuclear Waste Management Organization, given the waste that they hold at their 2 laboratories in Chalk River in Ontario and Pinawa in Manitoba. So the Nuclear Waste Management Organization, established in 2002 at the direction of a piece of federal legislation, and embarked on a siting process in 2010 to identify a, in quotation marks, willing and informed community to become the host for a deep geologic repository, a deep underground repository in which this 50 to 100,000 tons of highly radioactive waste would be placed. So there are 9 municipalities. At one point, we were up to 22 municipalities. As of 2015, the Nuclear Waste Management Organization continues to investigate 9 municipalities as possible burial locations for nuclear fuel waste. You might see on the screen a map that has those 9 municipalities identified. So it's the municipalities who expressed interest. But in Northern Ontario, there are 18 areas associated with those 9 municipalities. All of those areas are actually outside the municipal boundaries, and those are the areas that are actually under investigation. Depending on the stage, they're general potentially suitable areas or candidate areas, but those are the areas that are actually under investigation. For the 3 in northwest and southwestern Ontario, it is within the municipal boundaries that the NWMO has said they will investigate possible sites. So as part of the Nuclear Waste Management Organization plan, they have to transfer the waste. The waste would be shipped from the reactor stations, or in the case of ACL's 2 research laboratories, from those research laboratories in Chalk River and Pinawa, they must be shipped, then transported to the NWMO selected burial location. And that's where we're going to focus in our presentation today, is on that transportation of the high-level nuclear fuel waste, which would be required if the NWMO was ever to proceed and be approved and move to construction and operation of a deep geological repository. Some fairly large ifs there, but certainly possibilities that we can't afford to ignore. So the reference plan, the Nuclear Waste Management Organization has produced many documents focused on the transportation of high-level nuclear waste, the fuel waste. Initially, in what they called the study period from 2002 to 2005, they produced a small number of reports, and none of those reports actually discussed, acknowledged, evaluated exposure risk, dose to public or workers associated with the transfer of the transportation of the waste. More recently, they've produced a number of documents, and the more recent actually do discuss dose, and we'll be looking at them a little more closely. So these are the earlier documents you have on your screen, and they are conceptual design, lots of them focused on very general descriptions of transportation and on costing estimates. There was also an earlier report produced during the NWMO study period by the same utilities, Ontario Power Generation, Hydro-Quebec, New Brunswick Power, organized differently as a can-do owners group that did their first study on, or first publicly available study on cost estimates. And it was interesting because it used as their reference a 1,000 kilometer distance from the reactor, from the fuel location to a proposed or assumed repository location, which gives, I think, some insight into the industry's basic assumptions around their siting exercise. More recently, the NWMO has produced a number of reports that focus on issues around dose, design, and so on. Some of them still in the glossy brochure messaging kind of category. Some of them actually beginning to do some of the technical or approaching technical assessments. And we're going to look more closely at them. And of course, the most recent is a large glossy brochure, which delivers their key messages around the transportation of the fuel waste. So they began back in 2005, even in their initial final study, which was the 2005 report that recommended what they call adaptive phase management, which has as its endpoint a deep geologic repository. Even in those initial studies, the 2005 report did not spend a lot of time and attention looking at transportation issues, but they began the messaging that has carried through, which is that materials have been transported around the world for 40 years, no accidents that have resulted in releases of significant amounts of radioactivity. So the messages are around success. They are the success stories. Those are the messages through the NWMO documents. Then vary a little bit. Sometimes it's 40 years, sometimes it's 50 years, sometimes it's no significant amounts, sometimes it's no amounts that can be attributed to the transportation. So some careful messaging, transportation experience, the messages carry through. These are 2010 backgrounders. We hear frequently from the NWMO about the 1 million packages of radioactive materials shipped each year. Most contain medical isotopes, single isotope, most of them very, very short half-lives. So not exactly a fair comparison to fuel waste, which has a very high hazard level and has a very, 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 very long hazard life. But the messaging continues in the 2015, in the 2010 backgrounders, messages around it's not been transported widely in Canada. In fact, there's been very little transportation of fuel waste in Canada. There has been transportation of fuel waste primarily for the purpose of transporting fuel waste from a reactor station to the research laboratory. For example, when Darlington was observing Boeing in the fuel elements, they shipped some of those fuel bundles off to Chalk River for investigation. So we've seen estimates of either averaging 5 or 3 to 5 shipments per year. But again, they're single shipments. They tend to be a single fuel bundle or even a single fuel element shipped for research purposes, or the volumes that were shipped to Pinawa for research purposes at the Underground Research Laboratory in the 1980s. So again, nothing comparable to the kind of volume and frequency of shipments that we would see if the NWMO was to move into operation mode at a deep geologic repository. So one of the messages, of course, is that there's a strong international track record in transporting used fuel waste. 50 years, 20,000 shipments worldwide, and so on. And, key message is that we're to rely on that international experience. One of the challenges we have in Canada, not just in the discussion of fuel waste transportation, but more broadly, is that we have CANDU reactor design. 10% of the reactors in the world are CANDU designs, but we cannot necessarily rely on the analysis done in other jurisdictions of fuel waste transportation dose assessments, for example. So it's a bit of an additional challenge for us in Canada, because the messages from NWMO and the regulator are that we're to rely on this international experience. I just got a message that I lost voice. Is that the case? I think my mic is active again, so we'll continue. So we're told to rely on international experience, but we have a situation in Canada where we can't rely on international experience because we have a different fuel type. So that's a challenge we're going to touch on again a little later. So some of the materials that we're going to look at more closely now relate to the work done in the last few years by the Nuclear Waste Management Organization in developing their transportation options and assessment. So the NWMO now has a used fuel transportation package for people who are in the communities being investigated by the NWMO. You'll have seen the truck come to town a few times by now. So the NWMO has this used fuel transportation package. It is, in fact, a used fuel transportation package designed by Ontario Hydro in the 1980s, when Atomic Energy of Canada Limited was seeking approval for their deep geologic disposal concept, their idea of burying waste in the Canadian Shield. Ontario Hydro was basically their co-proponent and were responsible for transportation and siting. And Ontario Hydro, now Ontario Power Generation, developed a used fuel transportation package to put forward as part of that review. And in 2013, the Canadian Nuclear Safety Commission recertified that used fuel transportation package. So it was recertified without any opportunity for peer review, public review, or independent review. And we've not actually yet seen the documents related to that review. So this is what the NWMO version of that used fuel transportation package looks like when they're on the road. There is embedded in the middle of that long transport truck, which is actually a display booth and a display stand. There is actually a mock-up of the used fuel transportation package. The NWMO was saying in 2005, 2010, they were talking about transportation modes for used fuel would include road, rail, or water. More recently, they have focused on just road and rail and have not continued, at least in their documents, any discussion of the water option. And their basic assumption is that it will be a road transfer. And in fact, if the rail transfer includes road transfer. So for example, the fuel waste that would be coming from Bruce would go first by road to Godrich and move on to rail in Godrich, about 50 kilometers south, following down along the coast of Lake Huron. The fuel waste that would come from anywhere east, so Chalk River, Gentil, La Pro, would come by train to Mattawa and would come by truck to Mattawa and would be transferred to truck in Mattawa. So it would be first by road, then transferred in Mattawa, about 45 kilometers east of North Bay. So these are large parts of the project which have not been put really on the table by the NWMO, other than sort of as a fine print in one of their tables in their dose assessment reports. So their basic assumption is that it would be by road. And the numbers are fairly similar from 2005, 2010, 2015, in terms of the number, 622 shipments per year, 1 or 2 shipments per day. would be is a current estimate, and that would be for a 38-year period. That's the NWMO estimates at present. So they have the basics in terms of their reference plan, but it's very basic and it's very reference. The Nuclear Waste Management Organization and other nuclear proponents use this language of reference to say it's the plan in place for the present time. So they have reference case for the geological for the repository design, and they have reference plans for the transportation of the waste. And basically, it's a plan for the present time. So the risks associated. The NWMO has recently, in 2014, 2012 and 2014, done a series of reports specifically looking at dose assessment. And we're going to look more carefully at one of them than at the other two. But they did, in 2012, did a generic dose assessment for members of the public. So these are basically people along the transportation route, and concluded that there would be no significant effect. They also, in 2014, did a particular study on what's called the 9-meter drop test. So we've heard already that we'll be relying on international standards, international tests. And one of those is a set of tests. These are the safety tests that we're referred to, are the tests as set out by the International Atomic Energy Agency. And the tests include a drop test. There's a set of tests for what's called normal conditions and another set of tests for accident conditions. And the test for accident conditions, so this is the toughest test going for the drop test, is a 9-meter drop onto an unyielding surface. So perhaps as a result of people making some jokes, perhaps about the 9-meter drop test, the NWMO has come out with a special report on why the 9-meter drop test demonstrates equivalency to an actual real-life accident scenario. I would refer you to the report, but I, for one, found it unconvincing. The other report, and we'll spend a little bit more time on this, is the NWMO report on transportation worker dose assessment. And so the NWMO has released in 2014 a report of about 100 pages looking at worker doses. So these are they focus particularly on the driver dose, but also did some for auxiliary workers. So in this, they have a number of different assumptions that they worked from. So one of their assumptions was that the irradiated fuel had been out of the reactor for 30 years. They assumed that, and I just we're going to use as an example the driver with a 600-kilometer range trip. So 620 shipments of the year, there would be a limit of 86 trips for the 600-kilometer distance, or 45 trips for the 1,200-kilometer distance. We're going to come back and look at these a little more closely. They estimated dose only for the outbound trip. So this assumes that the rig is clean, that there is no residual or lingering effect on the return trip. Assumes normal conditions, so no accidents, no accident scenarios were considered in the worker dose assessment. It assumed an average burn up of 220 megawatts an hour per kilogram uranium. And we'll talk a little bit more about that. They assumed the driver was 8 meters from the fuel package. They made certain assumptions around distance, speed, rest stops, assumed that overnight stops would be spent outside the truck. And this is even for the longer trips of more, I think 1,900 kilometer was the number used. They considered only gamma radiation. So they assume that the used fuel package is absolutely clean, that there's no surface contamination, and in particular, no alpha contamination. They assume a 40-hour work week, which it's a unique trucker who works a 40-hour work week, but they assumed a 40-hour work week, and they used a representative model of the package, and they used a 2003 Monte Carlo computer code from Los Alamos Nuclear Laboratory. So those are all their assumptions that they used to arrive at their conclusion. So their dose rates, they had a number, so they have included in their report, they do provide their dose assumptions at different distances from the used fuel package. They have calculations for exposure times for different tasks within the trip completion. And they have driver dose summaries. And in the middle column within this, we see that the driver dose summary for per shipment is 0.0040, and their annual dose is 0.34. This is megawatt, this is millisieverts per hour. So just to take a moment and check those assumptions, and because this isn't an expert or technical presentation, and because we don't actually have an expert on hand who has to date been able to evaluate these reports, and that is one of the things that we'll come back to in next steps, and some of the needs that we have in terms of evaluating and peer reviewing some of these key materials. But just to check some of the assumptions. So the NWM was made. We can't do anything about the assumptions that they have built into the model. So they're using the Monte Carlo code. It's a couple of decades old, and we have the same challenges in that from a public interest perspective, as we do with any of these conclusions arrived at by the nuclear industry proponents when they base their findings on computer modeling. So first of all, you don't know the data, you don't know the models, you don't know the codes, and you're not the person running the model. So we can't do anything about that, but we can look at a couple of the more obvious assumptions, or less black box assumptions that they have made. So NWMO uses a burn up. They took an average of the fuels from the OPG reactors and arrived at 220 megawatt hours per kilogram of uranium. They also have a 280 number, which is the 95th and 99th percentile. If you substituted the 220, the 280 for the 220, you would have an approximately 65% higher dose. So I think there are questions around the assumptions when we've averaged the fuel and we're making an assumption that the fuel has all been out of reactor for 30 years. We've got a number of assumptions there, which could be pretty significant variables. The NWMO has also assumed that it's an 8-meter distance between the driver and the fuel package. So a 25% reduction in that difference would result a 2-meter reduction, a 25% reduction in the distance would, by my very layperson calculations, result in a 75% increase in dose. The NWMO also assumes a 40-hour work week, taking just a 600K trip, 600-kilometer trip, which their scenario was that's from Darlington to Elliott Lake. So presumably they mean one of the candidate areas north and west, or north and east of Elliott Lake, but they said Elliott Lake, so 600 kilometers. They calculated 11 hours, and they said a 40-hour work week. Well, if you went to a 44-hour week, you could increase your trips from 86 to 100. If you went to a 60-hour week, you could increase your trips to 125, which would be approximately a 50% increase in dose. So when you add those increases, you come considerably closer to the 1 millisievert limit, which is the regulator's limit on public dose, on dose for a member of the public. So if we were to reach that, they would be out of compliance with what is, by our understanding, already a quite permissive standard. 1 millisievert is the public dose limit, but it's generally accepted or generally assessed in the public interest community as being a quite permissive one. So not to come to any conclusions, but just to say, when we look at, when we look a little closer at the NWMO materials, we can see that there are a number of assumptions that have been made, which even from a non-technical perspective, we need to question. And I think if and when we get a technical review, we may have some additional assumptions that need to be really investigated. So looking at some of the non-NWMO material, and I've relied, there are a number of pieces of number of reports, pieces of literature that are available that are helpful. I've, for the purpose of today's discussion, pulled out only 3 of them. And the one that I actually find the most helpful is the radiation exposures piece done by the state of Nevada, Robert Halstead for the state of Nevada a number of years ago. And in fact, I'm going to rely on our summary of what's in the literature with respect to radioactive risks associated with nuclear waste transfer. I've also relied on Large Associates, a report done about 10 years ago, and the National Academy of Sciences has a report called Going the Distance, Safe Transport of Spent Nuclear Fuel. And we're going to just talk a little bit about some of the conclusions or some of the findings of these different reports. So National Academy of Sciences, I think, walks the line between the proponent's message of international track record, million shipments, normalizing this idea of transporting high-level nuclear fuel waste. They kind of walk the line between that and some of the more critical literature. And they say there's no fundamental technical barriers to the safe transport of spent fuel, high-level radioactive waste in the United States. When conducted in strict adherence to existing regulations, such transport is low radiological risk activity. It's manageable safety, health, and environmental consequences. However, there are a number of social and institutional challenges to the successful implementation. That success is based on several factors.